the lecture, because the meeting is much longer than I expected. Okay. So actually, this is the one we have. We have the total sum of squares, the treatment sum of squares, and the error sum of squares. All right. So you get something like this, and it is easy to observe that the SST, the red one is equals to the green one SSTR, the treatment sum of square plus the SSE, the error sum of square. All right, we have this equation, and this equation is called the fundamental equation of a node. All right, and this is basically the graph for illustration. Can you see it? So let's say this is the total sum of square. For the total sum of square, you get the difference between the variation of the observations around the grand mean. All right. For the treatment sum of square, you get the variation within groups. Okay, between the observations. Between the groups. Actually, you compute the difference between the mean of each group and the grand mean. And for the error sum of square, you compute the variation, the deviations of the observations around the mean value of each group. Okay, so the error sum of square can be used to describe the variation. I call it the variation within groups. Okay, within groups. And for the treatment sum of square, I call it the variation between groups. Do you understand? Is that clear? Okay. Is that okay, everybody? And here's the fundamental equation for a node, the one that I just mentioned. We have the equation that SST equals the SSTR plus SSE, and we can also find the degree of freedom. If you go back to this, there are 4 levels. So the degree of freedom for treatments is 4 minus 1, which is 3. Okay, and then there are totally 24 observations. Let's say capital N is 24. Then the degree of freedom of the SST should be 24 minus 1. So in this case, you get 23, right? 24 minus 1. And concerning the degree of freedom for SSE, it is simply the difference between the degree of freedom for SST minus the degree of freedom for SSTR, and that is 23 minus 3, you get 20. Do you understand? Okay, that's clear. And move on, everybody. Is this all right? Okay. So let's go back to our data set. This is the one we get, right? This is the one we get. And we can find the SST. We can find the SST. What is SST, by the way? SST is 7 minus the grand mean, which is 15.99 square plus, and then 20, this 20 minus 15.99, the grand mean all square. Okay. How about the SSE, in this case, is the deviations around the mean of each group. So it's 7 minus 10. All right, for the first group, 7 minus 10 square plus, and then you get 10, that 10 minus 10 all square. And then plus, for the second group, you get 12 minus 15.67 square plus, and then you come up with 15 minus 15.67 square. Okay. And then for the last group, what do you get? You get 19 minus 21.17 all square plus the last one, you get 20 minus 21.17 square. Do you understand? Okay. For the SSTR, the treatment sum of square, you get that is, what is that? You get let's say you compute the difference between the mean value of each group and the grand mean. So you get 10 minus 15.99, 10 minus 15.99 square. There are 6 observations in the first group, so there should be 6 terms here. You get 10 minus 15.99 all square. And then for the last one, you come up with 19 minus 21.17 square plus, for the last one here, you get 20. You get 20 minus 21.17 all square. Do you understand? Okay, is that all clear? Is this all right? Is this okay? Is this okay? So you can find the treatment sum of square, you can find the average sum of square, and you can find the total sum of square. The SSTR, oh, you think it is fast? Okay. For the SSTR, you get 10 minus 15.99, and because there are 6 observations here, then there should be 6 terms. So you get 10 minus 15.99 square, and then 10 minus 15.99 square, just like that. So you get 10 minus 15.99 square, and there are 6 terms like that. Okay, just like this. You have this one plus that one again, and then plus this one again. So keep doing that. 1, 2, 3, 4, 5, 6, just like that. Okay, is it clear? Is this all right? Is this okay? Okay. So so altogether, you can find the SST, SSTR, and SSE. There is another way to compute the sum of square. This is the definition we get. All right. This is the way that I mentioned. You can also find the sum of square by using a simpler formula. So instead of computing the derivation square, you can find the sum of square just like that. All right. So I'm going to compute. I'm going to use these expressions to compute the sum of squares. So let's go back to this. Okay, so you get 7 square plus 8 square plus 15 square plus 11 square plus 9 square plus 10 square plus 12 square, 17 square, 13 square, 18 square, up to 20 square minus the x square. So it is so you give these formulas to get the SAT. It is the sum of xij squared minus x squared. All right, and you get that one, and then SSTR, you get the average of the sum, right? The square of the sum. So you get 60 squared. You don't use the average value. That's the point. You don't use this one. You only use this column. So 60 squared plus 94 squared plus 105, 102 squared plus 127 squared, right? Divided by the number of observations in each group, right? Over 6 minus the x squared, the grand sum square divided by the number of observations, 24. Okay, do you understand? You should be careful with this sum. This is 60 squared divided by 6 plus 94 squared divided by 6 plus 102 squared divided by 6 plus 127 squared divided by 6. If there are only 5 observations in the third group, then this one should be 5 only. Understand? Is that clear? If you don't have a balanced design, then the denominator may be different. Is that clear? Is this okay? Okay. Okay, so after all, you get the SST, you get the SSTR, and then you can find the SSE, the L sum of square, by using the fundamental equation for A nova. So SST is simply SSTR plus the L sum of square SSE. And because we already knew the left hand side, you knew the first term on the right hand side, then you can easily find the last term by computing the difference between them, and you get that number. All right, okay. So the SSTR give you the variation between groups. Okay, and SSE gives you the variation within groups. So you come up with the variation within groups. You have the variation within groups, and if the variation within groups SSE is small compared to the variation between groups, so this gives you you can think of the SSTR, and this gives you the SSE. If the SSTR is too big compared to SSE, then you believe that the groups are far from each other. If the treatment sum of square is small compared or not too big compared to the L sum of square, then we think that the groups could be the same. Understand? So you want to compare the SSTR and SSE, or let's say you want to compare this ratio and 1. Okay, if that is too big compared to 1, then we say that we conclude that the groups are different. Okay, the means value, the means are different. If it is not too big, then the means may be the same. Okay, so in order to compute to know whether this is big or small, I need to know the distribution of this ratio. And in order to get the distribution, I should divide the numerator and the denominator by the corresponding degree of freedom. The SST, so you divide the SSTR by its degree of freedom, okay? And you also divide the sum of square for error by the degree of freedom for SSE, okay? In our problem, degree of freedom, the first degree of freedom is 3, and the second degree of freedom is 20, all right? And I will denote by F that ratio, this ratio. And if F is too big, then we will reject the null hypothesis. If it is not too big, then we fail to reject the null hypothesis. Do you understand? Is that clear? Okay. All right. How do you know if that is big enough? We say that it is big enough if F is greater than some value C. And in order to get that C, you need to know the distribution of F. And the distribution of F is a Fisher distribution. With 2 parameters. The first parameter is the degree of freedom for the sum of square for treatment. And the second parameter is the degree of freedom for the other sum of square. Okay? Sometimes we call it the F distribution. Okay, and then we can denote by F instead of Fisher, dF1 and dF2. Do you understand? That's clear? Okay. And the Fisher distribution looks like this. you come up with this one, all right, and you come up with that value. I'm sorry, you come up with this value, and we say that this is too big. You say that it is too big if f is greater than c. So we come up with the acceptance region, and the rejection region is over here, all right. And this area is the probability that you can make a mistake by rejecting the null hypothesis, right? So I would say that it is alpha, all right? And if you know alpha and you know the degree of freedom, then you can determine that value C, and you can compute this the f value, right? And you compare f and C. If f is big, greater than C, then we reject the null hypothesis. If f is not big enough, less than C, then we fail to reject the null hypothesis. Do you understand, everyone? It is okay. Any questions so far? Please feel free to ask questions if you don't really understand. Oh, by the way, we call the numerator here. We call the numerator here the mean square for treatment. We call it the mean square for treatment. And we call this one the error, the mean square for error. Okay, do you understand? And this is what you get. Okay, this is what we get. This is the mean square for treatment, and this is the mean square for error. And then we can consider the following statistic, f. And if f, then we have the following distribution. All right, this is the first degree of freedom, and this is the second degree of freedom. All right, and this is the summary of a so-called ANOVA table. And if we use the software to perform the ANOVA test, then we should get something like this. We will get something like this. We will not get the rejection region. Instead, you will get the p-value. So if you use the software, then we get something like the p-value, and then you compare that p-value with f. But if you use the table, then you come up with the following table, right? And this is called a ANOVA table. This is the trick for the source of variation, that is for treatment. So you come up with the SSTR right here, and you get the error sum of square, and you get the total sum of square, okay? And you can find the degrees of freedom, and then you divide the sum of square by degree of freedom to get the mean square, the corresponding mean square. And because we don't need the mean square, the total mean square, so we will not compute this ratio. We only need two mean squares, and then you get these two values, and you divide these two values to get the f value. And then you can use the Fisher distribution to find the critical point. And you compare f and that critical point. If f is too big, then we can reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. Okay. In our problem, we get the following table. We get the following table. So we get the degree of freedom 3. You already knew that. This is the degree of freedom 23. And you compare the ratio, the difference between these two degrees of freedom to get 20. And then you can also find the sum of squares, right? And you divide the sum of squares by the corresponding degree of freedoms to get the mean square. You get these two mean square, and you divide these two values to get the f value. Now we want to know if f is big or small. in order to get that, you need to determine the value C. And this is the value C. This is going to be alpha. Suppose that alpha is in our problem. Let me see. What is alpha? In our problem, alpha is let's suppose that it is 5%. So suppose that it is 5%, and you are using the Fisher distribution with 2 degrees of freedom. They are 3, 3, and 20. Okay, they are 3 and 20, and you can use the software or the tables to get that number. All right. I will show you how to find it using the Fisher distribution table. Okay, so you can see that we can see that we get the following table for the 2 degrees of freedom, and you have to be careful with the 2 degree of freedom, because if you use the wrong one, then you get the wrong answer. Okay, so you come up with the 2 degrees of freedom, 3 and 20. So new one is the degree of freedom for the numerator. Okay, so that is 3. For the denominator, you get 20. This is the value, and then you come up with the value 3.1, and that's why you get 3.1 up here. 3.01. Okay, you get 3.01. And then the value f you obtain is 19.6, which is greater than 3. So f is too big, and we can reject the null hypothesis, which means that we can conclude that the mean values are different. Do you understand? Is it clear, everyone? It is all clear. You have to be careful if you use something different. Let's say if we use the wrong order, let's say 20 for the numerator and 3 for the denominator, and then you come up with something different, 8.66. Okay, and this is wrong. This is wrong. Do you understand? And you should look for the F distribution. Okay, and you should also look for the F value, the alpha, which is 0.05 in this case. Is it okay? If alpha is 0.01, you should look for the appropriate table. If f is there is a question. If f is bigger than f, the critical point, but not bigger. Well, yes, as long as f is greater than f, you can reject the null hypothesis. Okay? As soon as f is greater than the critical point, we can reject the null hypothesis. It's just like what you did with the t-test and z-test, right? For the z-test, as long as the statistic belongs to the rejection region, we can always reject the null hypothesis. Well, there is no guarantee that it is always true. We can make an error with that conclusion. The probability of getting that error is alpha, right? Is 5% or 1%, and that is what you accept. Is that okay? Is this all right? Any question? Is there any other questions? Please feel free to ask questions if you don't really understand. That makes sense to you? It is okay. May I move on? May I move on? Okay. For now, what we can conclude is that we support the alternative hypothesis. It means that at least two of them are different, but you don't know which one are different, which one are the same. Okay, we get mu1, mu2, mu3, mu4. So mu1 and mu2 could be the same, and they are different from mu3, mu4, or mu2 and mu3 are the same, and they are different from mu1 and mu4, or all of them are different. You don't know. All right, and that is what we want to do now. In order to do that, first of all, you need to remember the model we have here. What is the model? Okay, so right here, how can we get it? Hello, can you hear me? Can you hear me? Actually, we want to estimate sigma square. And in order to get sigma square, you should understand the mean. Sigma square is actually the variance of the epsilon ij, right? It's the variance. And in order to get the variance, what is the variance? The variance is actually the average value of the square of the derivations. So it should be, right, it's 1 over something, the sum aside of the degree of freedom, to the sum of the square of the derivations. Okay, and then we can come up with we can see that is actually the sum of the xij, the observations, and the priming, right? The priming. Okay. I'm sorry, the mean of each group. So the xij minus the xi bar square. Okay. And you come up with this one, right? And you compute and divide this one by the corresponding degree of freedom. What is the top? The top is actually the SSE, the L sum of square, and the degree of freedom in the denominator is simply the degree of freedom of the SSE. Okay. Therefore, I get. Therefore, we have the. We can see that this is simply the MSE, right? The MSE. So I can approximate sigma square by the MSE. Okay, that is one thing the first thing I want to mention. Okay, now, if we have a look at the data set, this data set. If we have a look at this data set, then the mean value mi equals the average value 10 plus or minus the t distribution, right? The t distribution times the standard error. And what is the standard error in this case? The standard error is simply the square root of the variance, right? The MSE divided by the degree of freedom, the number. I'm sorry, the number of observations. And in this problem, for the first group, the number of observations is 6. Okay, so we get that one. And MSE divided by 6 in this case. In general, this is what we have. We get the approximation sigma square is close to MSE, and the mean is between xi bar plus or minus t alpha over 2 times the standard error, where the standard error is the square root of MSE over the ji. Ji in this case is the number of observations in the ith group. All right. In our problem, ji is 6. Okay, but if you have a data set like this one, then j1 is only 5, not 6. All right. Okay. Okay. We can always find the margin of error, which is t values times the standard error, and the t distribution here has the degree of freedom 20, right? We have the t distribution 20. That is this is the degree of freedom for the SSE, right? So we come up with we can find the value. We use the table to get 2.086. We use the table, the t distribution table with degree of freedom 20 to get that value 2.086. Okay, times the standard error. The standard error in our problem is the mean square, the square root of the mean square for error divided by the number of observations for the for each group. That is 6. So you get 6.51 over 6, and that is 2.1728. Okay, then you can find the degree, the confidence interval for each mean value. So mu1 is 10 plus or minus 2.1. mu2 is 15.67 plus or minus 2.1728, and so on. In our problem, all the groups had the same number of observations, 6. That's why they have the same margin of error. That's why we have the same error here, right? If you have different number of observations, okay, if you have different number of observations, let's say 5, 6, 4, then the number here is different for each group, and you have different margin of error, and you should have different errors. Do you understand? Is this okay, everybody? Is this okay? All right. Now I have a question. Can I just think about? Can I just have a look at the first group? Okay, because if I want to get a confidence interval for the mean value, and you have one group, you have 4 groups here, and I only focus on the first group. So for the first group, we get 10, the mean value, mu1 equals the mean value 10 plus or minus t value times the standard error. In this case, it should be the s over the square root of 6, where s is the standard deviation for the first group only. Can I do it that way? Can I do it this way? And the t value here can be obtained by using a t distribution with degree of freedom 6 minus 1, so you get 5. So I use the t value with degree of freedom 5, and the s is simply the sample standard deviation. Can I do it that way? Can I do it that way? Can I? Hello? Do you understand the question? Do you understand the question? We will study just 2 or 3 more minutes. Do you understand the question? You guys? I already told you how to get a confidence interval for the mean value by using the MSE, right? And then you get the standard error. But in the previous chapters, we already learned how to get a confidence interval for the mean value for a single sample, and I want to use that approach to get a confidence interval. Can I do it this way? Hello? Are you still there? Are you still there, you guys? Hello? Hello? Okay, and do you know? Can you tell me if I can do it this way? If I can find a confidence interval this way, like mu1 equals 10 plus or minus t alpha over 2 times s over the square root of 6. Can I do it that way? Or I can say mu2, or I should say mu1 equals 10 plus or minus the t value times the square root of the NSE over the square root of 6. And for this, I use the distribution with degree of freedom 20. What do you think? Can I use both of them? Actually, yes, you can use both of them. Okay, you can use them. Both of them are okay, but this one is better. Okay, both of them are okay, but the second one is better because in the first group, you try to approximate the error. You try to approximate the standard deviation. But in that case, you only use 6 observations, right? In the second expression, we use more than that. We use all observations. You use all 24 observations instead of only 6 observations. The more information you have, the better the approximation. Understand? That's why the second approach is better than the first one. Do you understand? Is that all clear, everybody? It is okay. It is okay. Okay. I think perhaps that's enough for today. Because I don't want to keep you so long. So that's enough for today. Next time, I will talk about the multiple comparison, and then I will move to some other design that you can use the ANOVA. And then I will finish this chapter, and then I will talk about I will move to the last chapter of the integration model. Okay. Yes. What is your question? What is your question? Yes, go ahead. For the deadline, it should be at least 3 weeks after I give you the I will make the announcements about that. And, at least 3 weeks. You should have at least 3 weeks for that. Okay. So anyway, it should be the end of the semester, and at least you should have at least 3 weeks to work on the project. All right, so you should have enough time to do it. Soon. In fact, I should give it before the holiday, but I couldn't make it on time, so I will try to make it soon, and then I'm going to give it to you perhaps this week. Okay, and there will be also a quiz that you can do. That will be about two sample hypothesis testing. Okay, and the deadline will be 3 days. I will mention the deadline on the beginning so that you can see it. Yeah, I mean, the same. I will mention that. It seems that you cannot see the information, so I will make it available for you, and then you can see it. And it should be 3 days. Okay. All right. Thank you very much.